Greetings, physicists. It's Mr. Gopal here. And in this lesson, we're going to talk about projectiles fired at an angle. This is part of Unit 2 on mechanics. It's day 17. The title is Projectile Motion for an Object Launched at an Angle. We want to be able to figure out when and where a projectile launched at an angle will hit the ground. And so this is a very interesting question. They give you the scenario of a cannonball fired with an initial velocity of 100 meters per second at an angle of 45 degrees above the horizontal. And then they continue to break down how this problem is solved and how we obtain a lot of information about the cannonball. I'm going to do a separate demonstration of all problems that are kind of like this to give you a really good outline on how to do it. So let's say now we have a cannonball. It's fired at 60 meters per second at an angle of 30 degrees. Let's figure out its maximum height. Let's figure out its landing distance from the launch point. Okay, so first I'm going to draw a little picture. All right, let's say that we launch from right here. And I'm going to put the ground in blue. Let's say that we have level ground to make things a little bit simpler. And we know that our angle is 30 degrees. And we know it's fired at 60 meters per second. So the first thing we have to understand is that for all vectors, all vector quantities that are vectors at an angle, we need to break our vector into two components. I'm going to do that in red. All right. In situations with projectiles, we're going to have a vertical vector and a horizontal vector. And now what we want to figure out is how to calculate those. So one thing that we can realize is that when we have these vectors, we can move this vertical one over and create a right triangle. And this is going to be very valuable. All right, because we have the hypotenuse of this right triangle, it happens to be 60, and we also have one of the angles. It's 30 degrees, all right, the angle between the base and the hypotenuse. Therefore, I know if I'm calling this y, so I'm going to change the color. I'm calling this y, and I'm calling this x, then I know that x is going to be equal to, or sorry, let me rephrase. The cosine of 30 degrees is the adjacent leg divided by the hypotenuse. So in this case, the cosine is equal to x over 60. If I solve for x by multiplying both sides by 60, I get 60 times the cosine of 30 degrees, and that's equal to x. Now I happen to know that the cosine of 30 degrees is 60, or sorry, the cosine of 30 degrees is the square root of 3 divided by 2. When I multiply these together, 60 divided by 2 is 30. So I get 30 times the square root of 3. And now is where I should have used my squiggly equal signs to say an approximation, because I'm going to round off. And I'm going to multiply 30 root 3. So square root of 3 times 30. That's going to be rounded off to 2 digits after the decimal point. It's going to be 51.96 meters per second. So that is the horizontal component of my velocity vector. Now to calculate the the vertical component. I know that the sine of an angle is the opposite leg in the triangle divided by the hypotenuse. So if I look opposite to 30, I get to y. And I know the hypotenuse is 60. So the sine of 30 is equal to y divided by 60. Solving for y, I get 60 sine 30 equals y. And now again, just like with the cosine of 30, I know the sine of 30. I know that it's 1/2. So I can say that equals 60 times 1/2. Or, and there I actually don't need squigglies because I can get an exact answer. That would be 30 meters per second. So I've got my two legs, all right? Y is 30, X is 51.96. So some good first steps happening. Now, in order to get farther, I need to turn to my, my reference table. And so what I'm going to do is I'm going to pull up and write on here some equations that are going to be valuable to us. All right. And these are our kinematics equations. So for example, I know that my final velocity is going to be equal to my initial velocity plus acceleration times time. I also know that distance can be expressed as my initial velocity times time plus 1/2 times acceleration times time squared. Use a caret to represent squared, right? And I also know, in addition to those, the following equation, that my final velocity squared is equal to my initial velocity squared plus 2 times acceleration times distance. All right, all of these equations are on page 6 of your physics reference table, and they're going to be very valuable to you. And what we're going to do is we're going to use them to calculate distance and velocity, etc., and acceleration. We're going to actually use acceleration, and I'll show you how, in order to figure out the range of this, or how far it travels horizontally before it hits the ground. And in order to do that, we need to take these equations and we have to break them down into x and y components. So let's say that my first thing that I want to focus on is the max height. All right. So starting off with my max height, that's what I want to figure out first. All right. In order to figure out my max height, I need to realize that there's a certain characteristic at some point when this hits its maximum height. All right, so let's say it's traveling along here and it gets up to there. And right here, I'll mark it in another color. I'll mark it in orange. Here's my maximum height. Now, the thing that we need to understand is that at the maximum height, my vertical velocity has changed from 30 to 0, okay? So that I'm gonna write as a principle for us to keep with us, all right? At max height, my final vertical velocity, if that's my final point, is equal to 0 meters per second. And that will always be the case for projectiles launched at an angle. Okay, and so if I know that, then I have a very valuable bargaining chip that I can put into an equation, all right? And I can start to figure out other aspects. So I'm going to start with this equation right here. And I'm going to use it to figure out time. All right. What I'm going to do is I'm going to take this equation. If I know that I'm using the vertical component version of it, I can say that VFY is equal to VIY plus AY times T. All right. And now the other thing that I need to realize in this case is that AY is acceleration due to gravity, or G, which is negative 9.8 meters per second squared. Okay, let me pause here for a second. I've done two very important things. The first thing that I did was I broke one of my kinematics equations into a vertical version, which is completely fair game. The other thing that I did is I recognized this projectile was fired on Earth. This cannonball was fired from a cannon on Earth, which means that the acceleration, the vertical acceleration of that cannonball will be acceleration due to gravity. So if I plug in these numbers into this equation, I'm going to get the following result. Again, I know that my VFY is 0, so I can put in 0 here. I know that my initial vertical velocity was 30. And I know that my acceleration due to gravity is negative 9.8. That allows me to isolate time. So I can subtract 30 from both sides. And that's going to give me negative 30 is equal to negative 9.8 times t. All right, my final step will be to divide both sides by negative 9.8. When I do that, I'm going to get, just calculating it right now, rounded to 2 digits after the decimal place, I'm going to get 3.06 seconds is equal to t. All right, so I've done one thing. I figured out how long it takes for my cannonball to get from the ground to its maximum height. And that amount of time is 3.06 seconds. Now, another principle that I can write out and keep with me is that the time to get to max height is equal to 1/2 the entire flight time, assuming that this cannonball is traveling on a level piece of ground. In other words, I fire it and I'm in a field, there's no elevation in that field, there's no cliff at the end where it drops off or anything like that. That means that the time it took to get to its maximum height is half of the time of its total flight. All right, so that means if this 3.06 represents the time to the maximum height, I can multiply it by 2, and I can say that 6.12 seconds is the time of the flight. Right? And so now I've got very valuable information that I can plug in. We are almost there, right? And we've calculated a ton about this cannonball already. Just bear with me. Okay, so the next thing that I want to do is go back and figure out the maximum height. All right, and for that, I need to take a few of the things that I have, and I'm just examining my equations. Let me see. We can take this equation now. Let's circle it in red. And I can plug in all the information that I know. So again, if I'm solving for maximum height, my time is 3.06 seconds. Okay, so I'm going to plug that in along with all the other values that I now know. And I'm going to say that d is equal to my initial vertical velocity, or dy is equal to the initial vertical velocity, which is 30, times 3.06, plus 1/2 times ay, which is negative 9.8 meters per second squared, times my time to maximum height squared. (30 times 3.06), that's equal to 91.8. (1/2) times negative 9.8 times 3.06 squared. All of that is equal to 45.88. Adding those two together, 45.88 plus 91.8. That's equal to 137.68 meters. So that is my maximum height. Again, the steps that I took to get it, first I figured out, or I realized that my final velocity at maximum height is 0. And I used that and acceleration due to gravity to figure out the time it takes to get to maximum height. My second step was to take that time and plug it into the red circled kinematics equation and figure out the vertical distance that it travels over that time using the initial velocity that I was given or that I calculated, and also acceleration due to gravity. So I've figured out my maximum height. Now all that remains is the landing distance. And for that, I need to use my x component or my horizontal component equation. All right, and so that one is going to be rather simple. I've already figured out, I'm going to circle it in green, that the entire time of the flight is 6.12 seconds. And now here is a beautiful fact that's going to make horizontal component equations so simple. Horizontal acceleration, or AX, is equal to 0 meters per second squared. In other words, the only acceleration on the cannonball is vertical, all right? There is no force acting on that cannonball in a horizontal fashion that is changing its horizontal speed. In other words, the horizontal initial velocity remains the velocity for the entire flight, okay? So I can break these equations down into their horizontal components and use them to figure out what is happening. So I'm going to take again this red equation. I'm going to circle it in green as well, because I'm using it again. And I'm going to move it down here and write out its horizontal version. And that would be that d sub x is equal to vix times t plus 1/2 a sub x times t squared. Couple things here. We know that acceleration horizontally is 0. So this entire second term, which I'm going to circle here in green, this is going to cancel out because it equals 0. All right. And so I know that dx is actually just equal to vix times t. Now, what is my initial horizontal velocity? Well, I calculated it before. It's 51.96. And what is my time? I need to take pains to remember that the time is the time of the entire flight. That is circled in green above, and that is 6.12 seconds. So when I multiply 51.96 times 6.12 seconds, I get 317.63. So there you have it. By first figuring out the time for the halfway point, which is at the maximum height, I then found the max height. And then I was also able to take that time, double it, and by realizing that the horizontal acceleration in the cannonball is 0 meters per second squared, I had a simple calculation of the initial horizontal velocity, or 51.96 meters per second, times the total time of the flight, 6.12 seconds, and that gave me 317.63 meters, which is the landing distance from the launch point. Sorry for my handwriting colliding with my type, but take a screenshot of this picture because I did several things. I broke my velocity at an angle into its horizontal and vertical components, and then I used a couple kinematics equations, my realizations about acceleration due to gravity, final velocity at the maximum height, and time to maximum height versus the time of the entire flight to calculate the maximum height and the landing distance of the cannonball from its initial spot. This process is foolproof. And as long as you keep these kinematics equations close and you pay close attention to the information that you're given, you should be able to ace what happens to be a set of very complicated questions. So we've done a lot in this lesson. We've been able to take simple information and figure out a lot more about the behavior of the cannonball. I hope this was a helpful video for you, and I hope that my explanation was clear. I look forward to working with you again soon.